And that's called psi of x. What do you do with it? Here's a formula. Psi star of x times psi of x. And these are wave functions now. These are not quantum fields. When I go to quantum fields, I will use large capitalized letters, even if they happen to be the same as this. What is that object? What does that correspond to? That's the probability to find the particle at x. It's the probability density. The probability density to find the particle at x. Right? Probability density. Prob-dense. You can fill in the rest of the letters. A fact about the probability density is that when you integrate it over position, what do you get? You get 1. It happens in this case that 1 happens to be the number of particles, isn't it? So you get 1, but you could also say you get the number of particles. Well, that's not very interesting because we only had 1 particle to begin with, and we were doing 1 particle quantum mechanics. Nevertheless, it's a true fact. Okay. Now, we next introduce a collection of 1 particle states that formed a basis, an orthonormal, orthogonal basis. Now, we can do that in a number of ways. First of all, the x states themselves are orthogonal to each other, and they form a basis. We'll come back to that in a minute. But there are many, many ways of choosing bases. Essentially, you take the eigenvectors of any Hermitian operator will form a basis. And in particular, if we're interested, we may be especially interested in energy eigenstates. For example, a particle in a box, that represents a box. The horizontal axis is the position. The vertical axis is the potential energy. When you get to the edge of the box, the potential energy becomes huge, and the particle just reflects off. It can't get through. In that case, the ground state wave function looks like that. The first example, we'll call that psi 1 of x. The next energy eigenstate looks like that. We'll call it psi 2 of x. And these are basically signs. Sign of, 2 nodes. And they're characterized by the number of nodes. Rather peculiarly, I started with psi 1, which has no nodes. Psi 2 has 1 node, but so be it. Psi I of x. And since these are supposed to be energy eigenstates, they're orthogonal to each other. They form an orthonormal basis. So let's write the equation for that. The equation for that is that integral of psi star I of x with psi j of x, that's the inner product, dx. What is that? Anybody remember? Delta ij. If I is equal to j, they're the same state. The inner product is 1, normalized state. If they're different, they're orthogonal, corresponding, let's say, to different energies. Sorry, delta ij, not 0, delta ij. That's another fact. Now I'm going to show you another little manipulation. This one, yeah.
So why does the probability density have that particular form?
That goes back to the postulates of quantum mechanics. The postulates of quantum mechanics said that probabilities, here's psi of x. This is the inner product of psi with a state localized at x. It's called the probability amplitude. The postulates of quantum mechanics, which I invite you to go back to, they're in the book, say that the square of that is the probability. So, okay, here's a little trick. A little mathematical trick that occurs over and over again. Take your orthonormal, your favorite orthonormal basis of functions. They could be sines, they could be cosines, they could be harmonic oscillator wave functions, whatever. Some collection of size which are orthonormal. Okay? And if they're orthonormal and they form a basis, then if you take this object, what is this object? This object is a operator. It operates on a state. Let's see what it does. Let's just explore what it does when it acts on a state. What does it do? If it acts on a state psi, then the beauty of the Dirac notation is you can just take the formula that you've written down here when you act with this thing on a state. Psi with I is a number. It's the inner product of psi with I times I. That's what it does. Now, here's a fact about any orthonormal basis. If you sum over all elements of the orthonormal basis, in other words, in this case, all the energy eigenvectors up to infinity, then what do you get? The unit operator, I, the identity operator. The operator that when it acts on any vector gives you back the same vector. That's a marvelous theorem. It's in the notes. And you should go back to it. Don't take my word for it. You can even prove it. But it's a useful thing to know. Okay, let's use that now in the following way. Let's take a project, let's act with this thing to the right and to the left. What we're going to do is we're going to take, and we're going to act, what are we going to act on? We're going to act on a state to the right, which is localized at position X. And on the left, we're going to act, well, actually what we're doing is I'm taking the inner product of a state with a particle at X with a state at Y. Everybody know what that the mathematical symbol for that is? The Dirac delta function. But let's come to that for a moment. Let's not write that down yet. Let's write that is equal to the sum on I, Y, X. All I've done is plug in the unit operator here. That does nothing. But now I have a formula here. The inner product of I with Y is psi I of Y. Let's see. Yeah. The inner product of any state with an eigenvector of position is the wave function of that state. Here the state is I, and it has wave function psi I of Y. There's over here psi I of X. And what does that have to equal? It has to equal delta of X minus Y. Sum over I. Yeah, there is. The second one. Yes, the second one. I assume that's what you were asking me. Yeah, the star. Okay, now we have a marvelous theorem. If we take any orthonormal basis, they could be the eigenvectors of any Hermitian operator, but in particular the energy, and you multiply for each one of those states, psi star times psi, and then sum over them, you always get a delta function. That's a good thing to know, as we'll see. It's useful. It means there's many, many ways of writing a delta function. Just take any orthonormal basis and do this. These could be sines and cosines. Sines and cosines are another way of writing a delta function. But And this is the basic mathematics. No more mathematics tonight. That's it, I think. Okay, now let's come back. Let's go to the problem of studying many particles all at the same time. Okay, now how are we going to characterize a state? One set of states which is particularly useful is a set of states in which you say how many particles there are with each one of these energies, for example. How many particles are there with state psi 1, psi 2, and psi 3, and so forth. And so we can take the multi-particle system and characterize